There was only one point in the history of the universe where everything happened at the same place in the same time, and that was the Big Bang. By definition, everything happened at the same place in the same time. And ever since then, the events have been getting out of sync, essentially, as things move apart and stop interacting. And that's where we are today.
Would time exist if humans didn't? So is time something that we construct as humans in the way that we interact with the world? Or is time something that's physically out there in the world? If we disappeared, would time still exist?
My name is Arkady Fedorov. I'm an associate professor at the University of Queensland. I'm a leader of the experimental laboratory. My lab is called Superconducting Quantum Devices Lab. We are interested in the limitation of quantum mechanics on timekeeping.
My name's Sally Shrapnel and I'm a senior lecturer at the University of Queensland. I work in the School of Maths and Physics. I think quantum physics, I don't think we know fully what it says about time at the moment. I know that there are, one of the things that we're exploring in this project is that whether our understanding of time from the perspective of what clocks measure. So one way of defining time is that time is what clocks measure. And when we try and build clocks using particles that obey the laws of quantum mechanics, what can we say? Is there anything different about these clocks? Is there anything about the physics of these clocks, the way entropy is produced? Are there any differences between those clocks that we build using quantum systems as compared to the ordinary clocks that we use, that we build using our everyday materials?
The clock is some kind of physical device which should count ticks or recurring physical events. And to count time, we need to count how many of these ticks happen before particular coincidences. So a good clock is a clock which counts very regular with high precision.
If you think about the nature of time as being what clocks measure, then there are two kinds of clocks that we're familiar with. So one are the kind of periodic clocks like a grandfather clock that we know that have a regular tick, and then there are what's called aperiodic clocks. So these are clocks that don't oscillate but usually instead rely on asynchronous tick, so the clock with no tock is what they're called. So radiocarbon dating is a form of this kind of clock where you just collect counts, and after a certain number of counts you know that a certain period of time has elapsed. So one of the really interesting things about this project is that the experimentalists have been able to tune between an aperiodic clock that can still measure time but measures time using irregular beats, all the way to the clock that is periodic and regular and like the grandfather clock. And they've been able to tune this experiment between those two forms of quantum clock, the aperiodic clock and the periodic clock.
My name is Jared Milburn. I'm a professor of theoretical physics at the University of Queensland. Most of my career has been dedicated to understanding the quantum world and quantum technologies, particularly quantum computing. But more recently, I've become interested in understanding the nature of time in the quantum world. To build a clock, any clock, including a quantum clock, you need to build an irreversible system with some sort of counter that's attached, where the counter inexorably gets bigger and bigger, 1, 2, 3, 4, 5. It never occasionally backtracks, it always keeps going up. A clock that occasionally went backwards would not be a very good clock. So the key thing you have to build is an irreversible device of that kind, very much like the pendulum clock with the little tick-tock oscillating ratchet sitting on top, giving it kicks. So in the quantum case, we need to build an irreversible system at very low temperature so that the only source of dissipation of energy is coming from spontaneous emission. So that's what we did. We built a very small antenna, essentially, out of superconducting metal, where electrons are just oscillating backwards and forwards creating a little dipole and radiate energy. We trap that radiated energy in a little flat, what's called a coplanar cavity. Basically, it's like a little sort of a flat microwave oven that traps the radiation, and a little bit leaks out, and that's what we measure.
So this is our clock, the superconducting quantum bit. So we build it on a chip. That chip has to be connected, to external world with wires. So through these connectors, the whole thing is attached to the cold stage of a dilution refrigerator and cool down to very low temperatures.
They can tune the machine so that it can operate in both of these regimes. So it can either be the aperiodic clock that measures time with an irregular tick, or it can be the periodic clock that measures time with a regular tick. And one of the really interesting things about this tuning process is that we can see that the entropy reduction is much higher for the clock that ticks regularly. So for once you get into that regime where you're putting a lot of work into the system, you're creating a lot of energy that dissipates out, and that creates entropy in the environment. So in one way, that's a way of linking this arrow of entropy and the arrow of time. As you get a more accurate, more regular clock, we have an increase in this entropy production.
The key point about these clocks, unlike a pendulum clock, which is driven by putting energy into the system, you have this falling mass which keeps kicking it and stops it from just sort of slowly decaying down to zero. So that's increasing the internal energy of the system. But there's another way to push it away from thermodynamic equilibrium, and that is to reduce its entropy. And this is something you'd never think about in an ordinary classical clock, but in the quantum world, because of quantum uncertainty, you can reduce the uncertainty or the entropy in the system by measuring it. Because if you measure it, you know much more about the state of the system than you would if you didn't measure it. So measuring it produces information. That information decreases the entropy or the uncertainty in the clock, and that is enough to push it away from thermal equilibrium in order to see the ticks. So in a very real sense, these clocks are not driven by batteries. They're driven by the act of observation alone. By extracting information in the right way, you can see it ticking.
FQxI in full is Foundation Question Institute. So this is a fund which is focused on fundamental research and answering big and even philosophical questions. So because our project is a proof of principle experiment which has a strong foundational focus, meaning how quantum mechanics affect timekeeping. FQxI was probably the best fit for this type of research, and of course we are very happy that we were able to succeed in this grant application.
From my point of view, I got into this to try and understand the nature of time and what time means in the quantum world. And now I think we begin to have an insight into that, and this will enable us to tackle one of the greatest unsolved problems in all of physics, which is how time appears in quantum gravity. We don't have a theory of quantum gravity. Einstein's theory of general relativity is a purely classical theory of gravity, but we know it has to eventually be consistent with quantum physics. We don't know how to do that. And part of the problem is understanding how time arises in a purely gravitational system when it's quantized. And I think our new understanding of how to build clocks at the quantum level will give us considerable insights into those fundamental questions.